Now we talk about the non-backtracking Laplacian, which gives an alternative way to study spectral graph theory. And I'd like to start with quoting this wonderful sentence that Joe Geraci wrote to me via email after I told him about these operators. The non-backtracking operators have made their way into my dreams. That's beautiful. So the idea of this setting is that we take again a simple graph G, and then instead of looking at the spectrum of operators that are directly associated with G, as we did before, we take one step forward. So first, we define the non-backtracking graph, which is a directed graph associated with the original graph G. And then we study the matrices that are associated with this graph. But the non-backtracking graph is a directed graph, and so the matrices are not symmetric. And so the spectral theory is much more difficult, but it's also really fun. So I hope you'll like this section. So this is how it works. We fix a simple graph on n nodes and m edges as before, and now we assume that it has minimum degree at least 2 because it makes sense in this setting. And then for each edge, we fix an orientation, meaning that we let one of its endpoints being the input and the other one being the output. And we let E1 up to EM denote the edges that have this fixed orientation. And it doesn't matter which endpoint we choose as input and which one we choose as output, as long as then we fix the orientation. And then we also consider the other orientations. And so we let EM plus 1 be the oriented edge that is the inverse of E1 up to E2M, which is the inverse of EM. Okay, so we take our simple graph and then we consider the 2M oriented edges and we order them in this way. Okay, and now we define the non-backtracking graph, which is also called the Hashimoto graph because it was introduced by Hashimoto in 1989, by the way, in a very different context, so not in the context of spectral theory. So it's defined in this way. It is a directed graph whose vertices are the oriented edges of our original graph. So it has 2M vertices that are these oriented edges. And then we have a directed edge from EI to EJ if and only if the output of EI is equal to the input of EJ and they are not inverse of each other. So in other words, if a random walker can go from EI to EJ following the orientation of these oriented edges without going back to where she was just before. So that's the idea, and that's why it's called non-backtracking. Okay, so let's start with two examples, which I think give better the idea of what's going on behind this definition. So first of all, boring example, we just take a cycle graph. Okay, so first thing we need to do to construct the non-backtracking graph is to fix an orientation for each edge, okay? So we let this oriented edge be E1, we let this oriented edge be E2, this is E3, and this is E4. And now the next step is to consider in the same order the inverse oriented edges. So we have E5, E6, E7, and E8. Right, so this is what we obtain. Here the vertices are the oriented edges from the original graph. And then we put a directed edge, for instance, from E1 to E2, because we can go from E1 to E2 by following the orientation and without going back. But we cannot put a directed edge from E1 to E5, for instance, because we cannot go from E1 to E5 following the orientation and without going back, okay? So this would be backtracking. We don't want that, and that's why we don't have a directed edge here. Now, why is this a boring example? Because we took a 4 cycle and we ended up with 2 4 cycles. So it's not very nice. And also, what's annoying about this example is that we started with a connected graph and we ended up with a disconnected graph. But the good news is that the cycle graph is actually the only case where this happens, where you start with a connected graph and you end with a disconnected one. So now that we have seen the boring example, let's look at a fun one. So we take exactly the same cycle as before, but we just add one edge. Okay, so as before, we fix the orientations. We let E1 be this oriented edge, then we fix E2, E3, E4, E5, and then in the same order that we just followed, we take the inverse orientations, okay? So we then take E6, E7, E8, E9, and E10. Okay, so now we are ready to construct the non-backtracking graph. So again, here the vertices are the oriented edges that we had here, so E1 up to E10, but now we have many more directed edges in the non-backtracking graph because we can follow many more orientations without going back. And two things that I want to observe is the first one is that now we are happy in the sense that we started from a connected graph and we end up with a non-backtracking connected graph. So that's nice. But also I want to observe that here we just added one edge compared to the previous example, but here we got many more directed edges. So why did this happen? This happened because one can show that if the original graph has n nodes and m edges, then the non-backtracking graph has 2 m nodes and this number of edges. Okay, so this explains. And by the way, showing this, I left it as an exercise in the lecture notes, and I think it's a good exercise because you need to think about it for some time, but it's not impossible. And I feel like once you are able to solve it, you really digest the construction of the non-backtracking graph, which could take some time to digest. So I think it's a good exercise to really understand the structure of this construction. Okay, so now we are ready to define the non-backtracking operators. So the classical one is the non-backtracking matrix, which is the adjacency matrix of the non-backtracking graph. So it's a non-symmetric matrix that is associated with the non-backtracking graph. And as the non-backtracking graph, the non-backtracking matrix was introduced by Hashimoto, not in the context of spectral theory, but later on the non-backtracking matrix also found its way in the spectral theory. And then Leo Torres was working on the non-backtracking matrix, and I was working on the normalized Laplacian when we met. And so we decided to define together the non-backtracking Laplacian, which is the normalized Laplacian of the non-backtracking graph. So it has the same definition as the normalized Laplacian that we saw for simple graphs, but it's defined for a directed graph. And in this definition, as degrees, we take the out degrees of the vertices in the non-backtracking graph. So yeah, we defined this operator, and then together also with Jürgen Jost, we started to study the spectral properties. So now I'm going to give you a summary of this. So first of all, the non-backtracking Laplacian has 2m eigenvalues, where 2m is again the number of vertices of the non-backtracking Laplacian, and it's also the number of oriented edges of the original graph. And these sum to m, and they are contained in this complex disk. Then the multiplicity of 0 equals the number of connected components of the non-backtracking graph, and this coincides with the number of connected components of G if none of them are a cycle graph, which is what I mentioned earlier. Then 2 is an eigenvalue if the non-backtracking graph is bipartite, which happens if and only if the original graph is bipartite. And the only difference with the simple case is that we don't have an if and only if for the eigenvalue 2. And then I know that this sentence is very vague, but I did that on purpose. Cycles leave signatures on the spectrum, which depend on the degrees of the vertices in the cycles. So why did I leave this vague? Because it's actually very technical. I also didn't put the details in the lecture notes. If you are interested in the details, you can look at our paper. But yeah, we have an entire section on this in the paper, and it's very technical. So I didn't think it would be helpful to put all these details. But what I want to tell you is that if you have cycles, different cycles in the graph, then they all leave the same signature in the spectrum of the non-backtracking matrix, but they leave different signatures in the spectrum of the non-backtracking Laplacian, because the signatures in the case of the non-backtracking Laplacian depend on the degrees of the vertices that are in the cycle. And this point is important because I think that it explains the fact that, as it seems, the non-backtracking Laplacian is much better than the non-backtracking matrix at distinguishing non-isomorphic graphs. Okay, so this is one important point, but again, sorry, I don't want to go into the details. And then another property that we showed is that the spectral gap from 1, which is similar to the definition that we had before, satisfies this bound. So it's always larger or equal than 1 over delta minus 1, where delta is the maximum vertex degree of G, and the bound is sharp. So in particular, 1 in this case cannot be an eigenvalue, and we always have a gap between 1 and the eigenvalues. Okay, and after we proved this bound with Leo and Jürgen, we were wondering whether we could also prove an upper bound for the spectral gap. So I did this then with Dong and Giulio in this paper, and in order to prove an upper bound, we had to define this new family of graphs, which will also appear in the last section, in the last video of this course. Okay, so what are circularly partite graphs? Given k larger or equal than 1, we say that a simple graph is circularly k-partite if the set of its oriented edges can be partitioned in this way, as V1 up to Vk, where the sets Vj are non-empty, and they satisfy the property that if Vw is in Vj, then the oriented edge Wz must be in the next class, Vj plus 1, whenever Z is not V. So as long as this oriented edge here is not the inverse of the first one. So for k equal 1, all graphs trivially satisfy the condition of being circularly one-partite, while for k equals 2, this actually coincides with the definition of bipartite graph. So we can say that circularly partite graphs are a generalization of bipartite graphs. And then this is one example with k equal 3. So you follow V1, V2, V3, V1, V2, V3, V1, V2, V3, right? So by following the orientations without going back, you always follow this periodic construction. Okay, so as I said, we define this family to give an upper bound for the spectral gap from 1, and this is the result that we have. If G is circularly k-partite, then the spectral gap from 1 satisfies this bound, and this quantity here is smaller for k bigger, so we are interested in knowing what's the largest k for which this is possible. And we have that equality holds for generalized petal graphs in which the petals have length k. And I think this is nice because it connects with the spectral gap from 1 that we had in the case of simple graphs for the normalized Laplacian, and for which equality holds in the case of petal graphs. Okay, and the last thing I want to mention about the non-backtracking Laplacian is this cospectrality table for small graphs, which was made by Leo, by my collaborator. So this represents the graphs with minimum degree at least 2, which are not uniquely determined by their spectrum by number of nodes. So here we have the number of nodes of the graphs up to 10. Here we have the number of graphs with that given number of nodes. And here we consider 4 different operators: the adjacency matrix of the graph, the normalized Laplacian, the non-backtracking matrix, and the non-backtracking Laplacian. Okay, so for instance, this 26 here represents the fact that if we take graphs on 7 nodes, then there are 510 choices, and there are 26 graphs that are not uniquely determined by the spectrum of the adjacency matrix. But if we look at the normalized Laplacian, then we just have 4, okay? And of course, the smaller these numbers are, the better the matrices are at distinguishing non-isomorphic graphs. So it was already known that the normalized Laplacian is better than the adjacency matrix when it comes to cospectrality. So this is why these numbers are smaller. It was also known that the non-backtracking matrix is better than the normalized Laplacian in this regard. But then what we showed is that at least for small graphs, the non-backtracking Laplacian is better than the adjacency matrix at distinguishing non-isomorphic graphs. And we believe, we conjecture that this holds also for bigger graphs, and we believe that the reason is behind this spectral property of the cycles that I mentioned earlier. And so this concludes the section on the non-backtracking Laplacian. And for this section, you actually have many open problems in the lecture notes. So yeah, see you in the next video.